Gnanam paramam dheyam. Knowledge is supreme.
Okay, so let us begin today's lecture by recalling that this last lecture we had proved the following theorem, that if A is a n cross n real symmetric matrix, 1 it has n real eigenvalues, and secondly if lambda 1, lambda 2, lambda k are distinct eigenvalues and ui's are corresponding eigenvectors, then the set u1, u2, uk is a orthogonal set. So, basically saying that for general for a given matrix, the eigenvectors are linearly independent for distinct eigenvalues. If it is a real symmetric matrix, then the eigenvectors corresponding to distinct eigenvalues are also orthogonal. So, using this, because it has already got n eigenvalues, and so there will be n eigenvectors, right, and we already know that because they are orthogonal, they are also linearly independent. So, the improvement on the previous theorem, which was for diagonalization, diagonalization of matrices, says the following, that if A is the real symmetric matrix, then there exists an orthogonal matrix P such that P inverse AP is a diagonal matrix, okay, and the diagonal entries are the diagonal eigenvalues of the matrix A. The column vector P are the eigenvectors of A. This should not be, are the eigenvectors of A. So, basically the same process that we do for general diagonalizability. Given a matrix A, you find eigenvalues, you find the corresponding eigenvectors, right. If it is real symmetric, there are going to be n eigenvalues, right, counting multiplicity. So, each eigenspace is going to have a basis consisting of eigenvector, right. So, but the only thing is that eigenvectors corresponding to distinct eigenvalues for real symmetric will be orthogonal, but inside the eigenspace they may not be orthogonal, they will be only linearly independent. So, what we can do is we can make, using Gram-Schmidt process, we can make those eigenvectors also mutually orthogonal. So, in each, for each eigenvalue we will have the eigenvectors, right, there is a basis consisting of eigenvectors because it is diagonalizable. So, we can find orthonormal basis, convert that basis to a orthonormal basis, and this says that for a real symmetric matrix this will always happen, right. So, for a real symmetric matrix there will be n eigenvalues, right, there is a basis consisting of eigenvectors, right, which are which form a orthonormal set, right. So, there is a basis consisting of orthonormal vectors. So, that is what is called the spectral theorem for real symmetric matrices, right. So, keep in mind, for a general matrix it may not be diagonalizable at all because it may not have eigenvalues. Even if it has eigenvalues, the algebraic multiplicities may not be equal to the geometric multiplicities, but for a real symmetric matrix always there exists eigenvalues. Algebraic multiplicity of each eigenvalue is equal to the geometric multiplicity, right, and as a consequence it becomes diagonalizable, right. Because it is diagonalizable, eigenvectors corresponding to distinct eigenvalues are mutually orthogonal, but inside each eigen subspace, right, the basis may not, basis exists, but it may not be orthogonal. So, we can use Gram-Schmidt process to make it orthogonal, right. So, that is the basic idea of this spectral theorem. The advantage is that this matrix P is a orthogonal matrix. So, for a orthogonal matrix, what is P inverse? You know, orthogonal means P transpose P is equal to identity, right. So, that means the inverse is the transpose itself. So, there is an advantage here that for a real symmetric you do not have to compute P inverse, it is just the transpose of the matrix P that you get. Okay. So, we will look at one example completely illustrating this idea. So, look at the matrix A with the entries 0 2 2, 2 0 2 and 2 2 0. So, first of observation is this is a real matrix and it is symmetric. So, the column here row here 0 2 2 is same as the column here. So, interchange rows and columns, this is a symmetric matrix, right. So, as our theorem says, it should have n eigenvalues, right. That means the characteristic polynomial should be completely factorizable. So, here the characteristic polynomial will be a cubic of degree 3, right. So, how do you find that? So, look at a minus lambda I. So, 0 minus lambda, 0 minus lambda. So, along the diagonal it will become minus lambda, expand that determinant. Okay. So, that determinant 3 by 3 you expand and simplify, it comes out to be minus lambda plus 2, lambda plus 2 and lambda minus 4. So, there are 3 factors, right. So, that means what? Lambda equal to minus 2 is repeated, it has algebraic multiplicity 2 and lambda equal to 4 has got algebraic multiplicity 1, right. So, for lambda equal to 4 there is not going to be a problem, because there is eigenvalue lambda equal to 4, we can find a eigenvector corresponding to it, right. The only work to be done is for lambda equal to minus 2, right. So, let us compute that. So, algebraic multiplicity of lambda equal to minus 2 is 2 and of lambda equal to 4 is 1. So, let us look at the eigenvectors for the eigenvalue lambda equal to minus 2. So, look at a minus lambda I, so that is a plus 2 I, right. So, that is easy to reduce it to row echelon form. So, that gives you 2 2 2 and 0 0 0. So, that means what is the rank of this matrix? That is 1, that means nullity is equal to 2, right. That means there is going to be 2 linearly independent solutions for this eigenvalue lambda equal to 2. So, how do you find that? We know the process. So, what are the variables which are non pivotal? X1 is pivotal, x2 is non pivotal, x3 is non pivotal. So, non pivotal variables will be given the arbitrary values and pivotal computed in terms of them, and because here its dimension is 2. So, the methodology is you first give x2 equal to 1, x3 equal to 0 and find out x1 in terms of that. So, that gives you 1, and second is put x1 x2 equal to 0 and x3 equal to 1, that gives you another solution for the same eigen subspace, right, a null space, and those two are going to be linearly independent automatically, because we have chosen x2 and x3 suitably. Okay. So, just writing this, that means it is 2 times x1 x2 x3, right, equal to 0, right, all linear combinations. So, that is a null space. So, you get 2 vectors, eigenvectors for this eigenvalue x1, x2 is equal to 1, x3 equal to 0, and similarly for x2 it is x2 is 0, the component x3 is 1, you compute accordingly the other one, that is minus 1 and minus 1. So, these are the 2 eigenvectors corresponding to the eigenvalue lambda equal to minus 2, right, and these are linearly independent by our choice of x2 and x3. The only problem is that these they may not be. See, if you multiply dot, what is the dot product of these two? So, that is minus 1 minus 1, that is 1 0 0. So, dot product is not equal to 0. So, these are only linearly independent, but they are not orthogonal. So, we will orthogonalize them. Before that, let us find for lambda equal to 4. So, a minus lambda I. So, along the diagonal it becomes minus 4, determinant reduce it to row echelon form, it comes out this. So, one row is 0, 2 rows are non-zero. So, the rank of this matrix is equal to 2. So, rank is equal to 2, nullity is equal to 1. So, only one dimensional null space. So, you can find that. So, how do you find that? For the what is the last equation? Minus 3. So, what will the last equation give you? Minus 3x2 plus 3x3 is equal to 0. So, what are the non-pivotal variables? Non-pivotal is only x3, right, third one. So, x3 is given arbitrary value, you find x2 from this equation, put those values back, you get the first variable, right, only one solution. Non-pivotal gets arbitrary values, others are obtained in terms of the non-pivotal. So, once you write that, you get, right, you put x2 equal to 1, x3 and you get 1 1 1. So, this is the eigenvector for lambda equal to 4. So, basically it is solving a system of linear equations, right, finding rank, finding nullity. So, you get 3 vectors x1, x2 and x3, right, and that will always happen for a real symmetric matrix. You will get 3 linearly independent eigenvectors, right, if it is if the order is 3 cross 3, n cross n, they will get n linearly independent eigenvectors for a real symmetric matrix. Now, in this observe, this x1 and x2 were the eigenvectors for the eigenvalue lambda equal to minus 2, right, and x3 is for lambda equal to 4, lambda equal to 4. So, x3 is perpendicular to x2 because they are for distinct eigenvalues, right, and x1 is also perpendicular to x3. You can just dot product and see that is equal to 0. So, eigenvectors corresponding to distinct eigenvalues will be orthogonal, but among themselves x1 and x2 are not orthogonal to each other, right. So, what we do is we know that x3 is orthogonal to these two. So, that is not a problem. So, these two we make them perpendicular to each other by using Gram-Schmidt orthonormalization process, right. So, what will be my first step? So, x1 is not perpendicular. So, we use, so if we are given these 3, how do you orthonormalize them? Gram-Schmidt process, from successively you are going to remove the projections, right. So, let us do that. So, define x1 and x3 tilde to be as it is, okay, the original ones, because they are perpendicular to x1, right, they are perpendicular to x2 is the one which is not perpendicular, x1 and x3 are perpendicular anyway. So, let us define that. So, x2 is the one which is to be defined now, right, either x1 or x2, one of them you can modify, so that it becomes perpendicular, right. So, you define x2 so that it is perpendicular to, right, x1, x1 and x2 are not orthogonal, right, from x2 remove the projection of x1 so that they become orthogonal, right. So, once you do that, so that is the way you x2 minus this projection onto x1, right, they were not orthogonal. So, remove the projection. So, once you compute it comes out to be this. So, Gram-Schmidt process, right, that is being used to orthonormalize. Okay. So, you get 3 vectors which are mutually orthogonal. Gram-Schmidt only give you orthogonal matrix, orthogonal, right. We remove the projections, you get only orthogonal, but you have to orthonormalize them if you want, right. So, then you divide each one of them by the norm of it. So, you can divide, so you get these 3 vectors, right, which are going to be, which form a orthonormal set. There are 3 of them. So, they will form a basis for R3, and each one of them is an eigenvector, right, because we have taken eigenvectors or only modified them. So, these are eigenvectors. So, what is the corresponding matrix that you will get? So, P, the matrix which is going to be the columns of P are going to be these vectors. So, first column is the first eigenvector, second column second eigenvector, third the third eigenvector. Process is same whether it is ordinary diagonalizable matrix or it is real symmetric. You find as many linearly independent eigenvectors as is the order of the matrix. If you are able to find, it is diagonalizable. If not, it is not diagonalizable. For real symmetric, you will be able to find 3 not only linearly independent, mutually orthogonal and orthonormal set of vectors which are form a basis. So, you get this, right. So, first column, second column, and that is the third column. And this matrix is automatically orthogonal because the columns are mutually orthogonal and unit length is 1, right. P transpose is equal to identity. Okay. So, there is this is a typo here, orthogonal. So, the inverse, right. So, P inverse is equal to P transpose. So, you can write P A P transpose is equal to diagonal, you can verify that. Okay. So, diagonalizability of a real symmetric matrix means first find the eigenvalues, you will be able to find as many as the order, right, unlike an ordinary matrix where it may not have any solution at all, right. There may not be any eigenvalue for a ordinary real matrix, but here for a real symmetric you will be able to factorize, right, and you will get n eigenvalues, some of them may be repeated, right, but each will have algebraic multiplicity same as geometric multiplicity. For a real symmetric, algebraic will be always equal to geometric multiplicity. Distinct eigenvectors corresponding to distinct eigenvalues will be mutually orthogonal. Inside, right, the eigenvectors corresponding to the same eigenvalue, you are able to find as many as algebraic multiplicity, they may not be mutually orthogonal. So, use Gram-Schmidt process so that you get orthonormal basis, right. So, that is the process. So, what are the applications? I think in the beginning I had said, once you are able to diagonalize a matrix, there is a lot of advantages in that. One is, supposing a matrix A is diagonalizable, that means there is an invertible matrix, so that P inverse AP is equal to D, right. So, if you want to compute powers of A, that becomes very easy, because if this is equal to D, then what is A equal to? That is P D P inverse, right. From this equation, if P inverse AP is D, then what is A? Multiply on the left side by P, on the right side by P inverse. So, you get A is equal to P D P inverse, right. So, what is A to the power K? So, it is P D P inverse to the power K. Now, when you expand it, what happens? When you expand, say 2, when you multiply, it will be P inverse here, and the next one will be becoming P D P inverse. So, P inverse will cancel, right. So, it is just the for any k, this power is P, the diagonal matrix raised to power k into P inverse. So, you do not have to do anything other than, if it is invertible, you find out what is the matrix D which is diagonal, right, which is the eigenvalues of the matrix A. Once you have found that, powers are very easy to compute, you have to just find D to the power k, and for a diagonal matrix, what is the kth power? For a diagonal matrix, it is just diagonal entries raised to this appropriate power, right. Is it clear? D square is nothing but the diagonal entries raised to power 2, Dk is diagonal entries raised to power k. So, this for a diagonal matrix, it is very easy to compute D to the power k. So, this becomes very useful tool, and this is useful when you are doing a lot of applications. For example, there is something called Markov processes, where this comes out as a probability. See, this matrix A is a probability matrix of going from one state to another of some process, right. So, if you are able to diagonalize that, right, and you want to apply that again and again and see what happens eventually to the system. See, okay, let me just give you an idea. So, there is a system which is being observed, imagine, and there are two possible outcomes of that system. System can, right, can go in one state or in another state. There is a probability, some probability that it will go stay in state 1, some probability it will go from state 1 to state 2, right, and some probability that it will stay in state 2. So, you can compute that, you can find that matrix, first entry will be stays 1 1, right, second entry in that row is the probability that from state 1 to state 2, bottom state 1 to state 2 and then state 2 to state 2 itself. So, that is where each row and column gives you a total probability of this. Now, what you want to do, this is the probability applying x1 x2, it will tell you where will x1 go, where will x2 go, right, with these probabilities. Now, if you want to apply again and again, right, then you want to compute if after k applications where will the system be, right, that means multiplying that x1 x2 by kth power of it, right, and eventually you want to know whether the system will stabilize somewhere or not. So, you want to compute higher powers of the matrix, probability matrix that comes there. So, this has applications in many stochastic modeling and such things. So, we will not go into that, but idea is that once it is diagonalizable, powers are easy to compute. So, that is the advantage. And you will see in your course in differential equations, you may have to compute what is called the e to the power of a matrix, exponential of a matrix. You know, given a number you can compute e to the power x, right, but how do you define what is e raised to power a matrix A? So, if it is diagonalizable, e raised to power xt is very easy to compute, right. So, e raised to power x A you can define if it is diagonalizable p e raised to power the diagonal matrix, okay, and e raised to power diagonal is very easy to compute. If the entries are lambda 1 lambda 2 lambda n, then e raised to power d is just diagonal entries raised to power that, e raised to power that, right. And this happens actually not only for exponential, for any function of d, you correspondingly look at f of lambda 1 and f of this. So, diagonalizability has a lot of applications in computing functions, right, when the domain of a function is a matrix. Exponential is one which most probably will come across when you look at systems of differential equations and finding solutions. So, eigenvalues and everything will come back there. So, the one advantage of diagonalizability that you can compute powers and the functions of